Okay, very easy, simple. So like I mentioned, the sets do not have to just contain numbers. It could have either, like for example, names or name of people in this class. Now, what would these stand for? T, 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 TF, TFT. True or false? But why in combination of 3? What does that mean? So we have true, 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 false, true, false, true, true, false, 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 true, true. So this is a set of what? So if you cover probability in your stats course, then you would know. For example, it could be an experiment to roll your dice or flip a coin 3 times. So head can be true, tail can be false. You flip it 3 times, then you have 3 outcomes. And this is one event. So you can say this set consists of the events in an experiment that you flip the coin 3 times. Or we can say, consists of an experiment to say, true or false, you have attended this class in the first 3 lectures. So if you are here, all 3 classes, you'll be true, true, true. But if not, maybe someone was sick initially, they could be false, false, false. Okay, so it can represent different things. But basically, it's a set of 3 independent events that's described here. That has outcomes of true or false, binary. 2 outcomes. Yes or no, true or false, male or female. We can also say, first 3 students who came to class today, is it male or female? I saw 1 female and the rest were male. But I'm not sure who the first 3 were because there were more than 3 of you when I came in. Okay, so there's different ways to describe experiments, and we can describe these outcome in form of a set. A, B, A, D, B, D. So what could that be? Can you give me an example? What do you think that can represent? Let's go to the last one first. Maybe it's easier. Last one's called an empty set. There's nothing in it. It's blank. So it's a special property. It's called an empty set. Okay, what about this one? We have embedded sets. So each element is itself a set. It's possible, right? Because we have different elements in a set. But each of these elements can be different things. It can be a number, it can be a name, any kind of object which includes another set. So here we have an embedded set as the elements in this set. So can you give me a practical example why we might have this? Can anyone think of an example? Are most of you a morning person or late night person? In other words, are you awake? How many of you are awake? Because I saw one person who was already sleeping when I first started my lecture. And he's currently out of the room. Okay, maybe I should ask this another question first. How many of you understood my question about this? Okay, a few hands went up. You understood, right? So can you give me an example? I mean, any scenario, doesn't matter. So this describes subsets of two sets, two sets, two sets. Okay, maybe let's go to another thing. We have someone just come in. Did you have breakfast yet? Hello? Have you finished eating breakfast? Did you have breakfast? What did you have for breakfast today? Cracker and peanut butter. Okay, we have two things here. So A are crackers and B is peanut butter. So anybody else here have cracker and peanut butter for breakfast? No? So he's unique? I'm sure sometimes some of you would have crackers and peanut butter maybe, but maybe you're allergic to peanut butter. I don't know, it's possible. So you could describe breakfast items if you want. We're limited to two things, or two main things. I mean, there are many things you can actually use this kind of notation to represent or to denote. Okay, more definitions. So the first one we saw is a small x is an element, capital S is a set. And we say small element x belongs to a certain set, it's an element in there. So now let's say we have two sets, A and B. Just like here, A and B. Okay, capital letters. If A and B are sets, so maybe it could be sets of crackers, different brands of cracker, types of crackers, a set of peanut butter, maybe different brands of peanut butter. So it could be different examples. We use another notation. A reads is a subset. So this notation here, like not the one with the belonging to, but with the underscore bar here. But you can see that, you can say this is a subset of B. So B seems to be bigger because it's belonging to this side, and A is a subset of B. So let me ask you, is cracker a subset of peanut butter? Sorry? A is cracker, for example. B is peanut butter. Is cracker a subset of peanut butter? No. No? Yes? That's a notation. I say if, say these are sets. We use this to denote that A is a subset of B. That means every element of A is also an element of B. And peanut butter and cracker normally are quite different. At least the brands would be, unless you can say there's a monopoly. Everyone makes crackers, also make peanut butter. Depends on what you look at. You can also argue maybe some crackers, maybe it's a peanut butter cracker. It contains peanut butter inside. There may be some overlap, but it's not a subset. Okay? Not every element of A is an element of B. Okay? So here are some practice questions. This would be easier to do than what I just asked you, probably. Okay, I already heard someone say false. That's good. So is this a subset of this? Not. But what about the reverse? The reverse is true, right? because 2, 3, 4 are here. Okay, I guess before you can do this, you need to know what these special notations are. Anybody know what Z stands for? Integers. Q? Rational numbers. Natural numbers. Okay, now do you know what they are? So is this true? First one. First one should be true, right? Integers are rational numbers. All integers belong to natural number. Should be the opposite, because natural number only positive numbers and contains 0, right? But integers can be negative. What about this one? True. So an empty set is a subset of any set. So theoretically, it's possible that no one will show up for my class, right? That will be an empty set. And this one? True. And the last one? Tricky, right? We're talking about the subsets here. A, is A in here? No, this is not A, this is not A, this is not A. It should be put in parentheses AB to denote one single element. So when we put it in this is a set. Consists of two elements, A and B. So if we say element A, does it belong in here? It does not belong in this set, because this set consists of sets itself, not single elements. Okay, so this is a trick question, you can say, a bit tricky. So you have to pay attention. If you're sleepy when you're doing a test, you might miss it and say, oh yeah, this is an element here. So just be careful. So far, if you do a quiz, seems like most of you, we got perfect. No problem. Okay, so next, let's move on to notations for sets. So if we have a very large set, so far we described very relatively small sets. Anybody remember the sets that I've shown you so far? Another trick question. How many elements, what's the largest element in those sets that you've seen? Testing your memory. How many sets have I shown you in the example in the slides? You can go back on your slides if you have it. Many, right? Show you maybe up to 10 sets. So what is the size of the largest set that I've shown you? Another trick question. You know what a trick question means? Do you know what I mean when I say it's a trick question? You know what a trick is? Do you play tricks on your friends? Sometimes? Well, teachers play tricks on you too sometimes. Especially in tests. So those will be considered trick questions, because you have to be careful. A trick is If you just do your normal things, chances are you'll miss the trick. Well, most of the sets I described so far are not large sets, except for these, which actually we haven't described the whole set, but we just describe it in words. So we're going to use what's called, for large sets, a more compact, easier to, you can say, notation for a set builder. So here we will have, you have seen the left-hand side here before. So small n means it's an element, right? Before I use x, but this time I use an n, denote an element. N is an element in integers, in a set of integers, right? Now, the set notation, we're going to build on the set, the condition. We put a new constraint. So let's start out with a set of all integers, but we said this number, this integer, is divisible by 4. So now we narrow it down. So not only an integer, we said it's an integer that is divisible by 4, which would be the elements in this set. So examples, what's divisible by 4? 4, 8, 12, 0, minus 12, and so on, right? So those are divisible by 4. So what's the size of this set? How large is the set? Yeah, how large is it? Can you count it? It's infinite, right? It's an infinite set. Because it goes to positive infinity, it goes to negative infinity. You divide by 4, it's still infinity. Unless you multiply by 0, but we're not doing that. Okay, what about this one? So this is a property, you can say, in terms of a form, we'll say 4k, so k again, denoting an element, right? You can say the 2 dots can also mean such as, or such that. So this and this, are they the same thing? No? Well, it says k. Okay, let's extract the elements. So you know the elements here, right? What are the elements here? So you would say the set consists of 4 times k. And k belongs to the integer set. So let's start out with integer 1. So the element with k is 1, the element would be 4. When k is 5, the element is 5 times 4, 20. When k is 0, the element is still 0. So now if you compare the elements of these two sets, are they the same or not? You compare the elements of these two sets. It would be the same. I mean, write them out if you want, just a few of them. Start from 0, goes to, say, plus 100 or plus 10, up to 12, I guess, and minus 12. Do those for these two sets, and you'll find that it's the same. So all it shows you is that there are different ways to describe anything. There's no right or wrong way, but you have to understand it. You have to understand what notations, the meaning, and you have to understand, I guess, later on we'll be talking about manipulation, working with sets. So like you are set, I'm working with you right now. I'm working a set. I'm actually manipulating this set too right now. Any questions so far? Is that clear? I'm going pretty slow. For me anyways, I'm going pretty slow. Okay, right? So do not worry if it takes a bit longer than other people to understand. But just make sure you take the effort to understand what we have presented so far, because it's not difficult, but it could be a bit tricky, some things. And some of you might have problem understanding some of the concepts. If that's the case, you could just raise your hand in class or talk to me afterwards. You can send me a message on Emoto. I won't promise I answer all of them, but I'll try to. Or ask your friends, of course. That's the easiest thing. But make sure your friend understands too. Because sometimes your friend thinks they understand, but when they explain to you, then you get confused. Because actually, they may not fully understand. So you have to be aware of that. Just be careful. Okay, so now we go to this, which we described. It should have been earlier. So n is a set of natural numbers, starts from 0. Z is a set of integers, goes from negative infinity to positive infinity in terms of integers. And Q is a set of rational numbers. And R is a set of real numbers. So what is the most common real number that you know? Actually, any number is a real number, right? So are you going to say 100 maybe that you'll get in this course? 7? Is a lucky number? Okay. But some of you may say pi. Pi is not this, pi is not this, pi is not this. But it is here. What is pi? Not the life of pi, but pi. Have you seen the movie The Life of Pi? You read the book. Because when I look at you, then it's Life of Pi. Some, I guess, resemblance. Okay, pi is kind of a magical number. You will see that in functions and relations later for sure. You know what pi is, right? Okay. So just to keep you awake, another person is kind of eyes are closed. So list 5 members of each of these sets. So notice we use the set notation, this, and then we have colon, this. So all of these are numbers. Okay, so let's start with the first one. Give me 5 numbers. 4. 16, okay. 8, I'm not sure. Who said 8? Do you understand? What is a perfect square? Okay, so it's like 2 squares, 4. 4 squares, 16. Well, when in doubt, I mean, you're free to use the internet in class, especially, for class purpose. But if you do other social media, keep it whatever, I guess I won't stop you. But so if you need to find out, for example, what is a perfect square, because you don't understand, then you just very simple. It's a number that can be expressed as a product of 2 equal integers. Okay? So if you have a question, if you don't understand what this is, especially in a midterm, raise your hand. I guess you won't have access to internet, but we do expect you to know things like this, but just in case, you need to clarify. Read it very carefully, the wording. And don't just assume. If you assume, at least put it down, I assume perfect square means this. And then write down your answer. At least you'll get some marks for it. Okay, so be careful. Read the questions very carefully. And make sure you understand what it is. So perfect square is a number that can product 2 equal. For example, 3 times 3. Or 1 is a perfect square too, 1 times 1. Or 0 times 0. Okay, so we got the first one done. What about the second one? One, 10, 1, 4, 7, 10, 13. Okay, that's 5. That's good enough. Easy, right? So sets of integers such that x minus 1 is divisible by 3. Of course, we can express this another way, right? But this is probably easier to understand. So we try to give you things that are easy to understand. What about this one? One over 2. 1 over 3. 1 over 4. Okay? So those all would be, if you square those numbers, they're all less than 2, right? Last one. Pi, 0, 2 pi, 3 pi, 4 pi. Okay, so you know pi. Okay. So now this is a bit trickier, or another way to represent things. So we're using the set notations. Give me 5 members of this, the first one. Okay, I heard 1, but 1 is not correct, right? It's 3, okay, 3. 12, okay. 24, no. 27, yep, okay. 48, okay. 0, good, okay, we have 5. So do you all know how we get those numbers? Anybody not know how we get those 5 numbers? You all know, right? So it's easy to do a quiz after the break. You would all get perfect. So basically, we just pick numbers here. It's like 0, 1, 2, 3, 4, 5, substitute in here, and then we present the numbers as members of the set. So this is 0, this is 0. This is 1, this is 3. This is 2. 2 squared times 3 is 12, and so on. So you can list 5 members easily. So the same thing here. Now we restrict to natural numbers. Okay, so just be careful. Natural numbers start with 0, 1, 2, 3, 4, and so on. So can you give me quickly 5 numbers for this, or 5 members of this set? 1, 9, 1, 5, 9. 13, 17. So it's the first 5 elements. Right? Just put in 0, 1, 2, 3, 4. Plug it into here. You get 1, 5, 9, 13, and 17. Okay? Okay, last one. Now we have 2 conditions. So R is a rational number and between 0 and 5. So just to let you know, integer. Are integers, maybe I should ask you, are integers rational numbers? They are a subset, right? Integer is a subset of rational numbers. Because 1 can be expressed as 1 over 1, for example, or 2 over 2. So if you want, the easiest way is just to, you can just ignore it. Q just says integer. It's quicker calculation, but it's up to you. Anything is fine. Can someone give me 5 numbers here? Three. So is 0 a rational number? Can be 0 over 1, right? Okay, so it could be 3, could be 1. What else? Minus 1. Minus 3, yep. One more. Minus 5. Actually, those would not work. Oh, yes, it would. Always between this and this. Okay, fine. Yep, that's correct. That's fine. So now, once you list, the other thing you should do, once you list your members, check to make sure they satisfy these conditions. Okay. Just to double check. Doesn't hurt, because sometimes you can make careless mistakes. Usually you have more time than you need in a midterm. Most of you just sit there, oh, I'm stuck, I cannot think of to do anything, and just sleep or rest. That means you have time to check your previous work. Just make sure they're correct, at least. So there's always time. There's enough time in midterms. How many of you left your midterm early for this course? Anyone left early? Anyone want to admit they left early? In your midterm last week, I guess, for this course, did any of you leave the exam before the end? One person? Okay. I hope that means it's not difficult. All right. Next, we're going to talk about set operations. So what can we do with sets? Like with numbers, we can add them, we can subtract them, we can divide them, and so on. So what do we do with sets? So the simple ones would be looking at things, you've seen these symbols before. Intersection, we're looking at elements that are common in two sets. A and B, for example. What are the common elements, or all the common elements in sets A and B? Union means or, that means all the elements in A and B, all of them combined. And then A minus B means it's in A, but it's not in B. So these are some of the operations. Some of the things we can do with one set, with another set, or with more than one other set. Okay, so you have seen these kind of things before, right? Union, intersection, subsets I talked about before. We also have complement. We just use a prime for apostrophe, but it's a little prime on top to indicate a complement. The complement of a set means is anything but that set. A complement. Yeah, so we have a comment here that A minus complement of A is a 0. Well, why don't you tell me? A minus A prime, is it equals to what? Well, we have people saying A. So A and A complement are completely separate, right? There's no common between A and A prime. So we also introduce a notation called partition later. So actually that forms two partitions, A and A prime. They're separate. So there's nothing common. So A minus this is still A because there's nothing in here that's A. When you subtract something that's 0, you can say, you still get A. So what you are saying is this. Was that right? So there's nothing in common between A and A prime. At least in terms of elements of the set. Okay, let's do a little practice before we take a break. We'll do some simple operations. So here we introduce another concept. We have subsets or sets of A, B, C, D, but they belong to, we call it the universe. That means the whole thing consists of only numbers from 1 to 10, integers from 1 to 10, or natural numbers from 1 to 10. So the whole universe, only that. And each of these are subsets of this universe. Okay, let's start with the first one. A and C. What is A intersect C? 3, 5, 7. Okay, so 3, 5, 7 is common in sets A and C. B or D? 2, 3, 4, 5, 6, 7, 8, 10. Right? So 2, 3, 4, 5, 6. Oh, sorry. B and D. 2, 3, 5, 6, 7, 8, 9, 10. Okay, I'm wrong. You're right. See? Good, some of you are still awake. I'm already sleeping. So it's 2, 4, 6, 7, 8, 9, and 10. All right. Good. So it's easy, right? Even though you can even tell when I'm wrong. 3, B minus D. 2 and 4. So what's common is these 3. We take these 3 out. So it's 2 and 4, right? Okay, B prime. Okay, so basically 1, 3, 5, 7, 9. So you can also say A is the odd numbers, B are the even numbers, if you want to describe it in words. Okay, 5. A union B minus, and then minus C. 1, yep. 4, yep. 6, 8, 9 as well, and 10, right? So we just combine these two as in one set, and then we subtract these elements from that set. So nothing difficult, right? 6, A union C intersect B. A union C intersect B. A union C intersect B. So we have 2, yes? Only 2? Okay, only one number 2. Because this consists of only one even number. And B is a set of even numbers. It's only 2. Okay, that's good. What about B prime, B complement, intersect C complement? One, yes, 1 is there. And 9. So the easiest thing to do is do this first. I mean, just to be sure. What's B complement? B complement would be 1, 3, 5, 7, 9. what is C complement? C complement would be 1, 4, 6, 8, 9, 10. And then we take these two sets, find the common elements, you will see there are 1 and 9. Okay, just do it step by step to make sure. Like I said, you have time usually, so that's not a problem. Okay, B union C and then the complement. B union C and then complement. Only 1 and 9. Is it? So do we have the same results, 7 and 8? 7 and 8 are the same? That's one of the properties. We will talk about this after. 7 and 8 give us the same results. Okay, what about 9? C intercept D, these two. Common would be 7. Minus A is 7. So C and D, right? So what's the answer for 9? Empty set. Because when you say the intersection of these two is the digit 7. And you subtract off what's in A, 7's in A. So you subtract 7 from 7, you have nothing left. So it's an empty set. The last one, B intersect D prime. B intersect the complement of this. 2, 4. Is it? Yeah? Yeah, looks like 2, 4, right? Okay, it's just 2, 4. So how many of you understood all 5, all 10? I hope more hands will put up. How many understood more than half? I think all of you will raise your hand. More than half includes, you know all, right? More than half is more than all is a superset of all. All right, so maybe you're already taking in a lot of information today. Like I said, mostly review, so we'll take a break. Come back in 10 minutes. And we'll take attendance after we come back from the break. Okay, I guess it's been more than 10 minutes. I'm just trying to set something up. That's why I haven't started yet. Okay, because I'm showing you how I can create a survey here, which you'll be answering. You can start working on this simple. Okay, for the last question here, which I'll pose and ask you to do, what do you want to know about your class? I can ask. Sorry? No, what do you want to know about your class? Anything you want to know about your class? Nothing? Not curse. Oh, what happened? Oh. Okay, I think it's posted. Go to Edmodo. Instead of, actually I should have called it an assignment, I guess. Can you check your Modo and then see if you get this note and then click on the link to answer the survey. So if you click on this link, it should get you to this. So you can answer this. I know it's not easy to type on the phone, so it take a little while to answer some of these questions. Other subjects, I mean other courses that you're taking this semester, or that you have taken, whatever. So how many people finished the survey? Still typing? Yes. Yeah, there's a question, can you submit it again? Yes and no. But since this is not a quiz per se, so don't worry about it, I would say. But if you want to submit it again, you need to submit with another device. Because your same device will not let you do it again. So I guess some of you are done because you're walking out, taking another break. Okay, I'll give you 2 more minutes, then we'll continue. Okay, time's up. Please submit. I'm going to close it. If you haven't done so, please submit. Because I'm going to close this survey. I will close the survey. So if you don't submit within the next 15 seconds, you cannot submit. Five, 4, 3, 2, 1. Just a minute. Oh. Do you mean a whole minute? Done? Okay, I'm closing it. Close. All right, done. So for number 4, what is the answer? What's Q or N? Q. What is Z union or union of Z and Q? Q. So what's the complement of Q? Q prime, yeah, okay. What is that? Irrational numbers. So what are irrational numbers? How do you express irrational numbers? I haven't shown you. Something you cannot represent in a fractional form. It's not rational. So irrational number, sometimes you see represented by the set capital P. And capital P, irrational numbers, is real numbers minus rational numbers. So real numbers is all the numbers, including rational and irrational. But it does not include complex numbers, which we haven't talked about, but it's okay. So irrational numbers is basically real numbers subtract rational numbers. And those are irrational numbers. Does that make sense? If you're not rational, that means you're irrational, which means not rational. So pi is an irrational number. This is an element of irrational number. Okay, so I'll move on with the rest of the lecture for today. And I might move a little bit faster. Let's see if you can catch up. So next is visualization. How can we visualize, how can we represent sets of numbers? One way, common way, is called a Venn diagram. V-E-N-N, Venn. Basically consists of circles. So each circle is a set. So it's showing here overlapping between sets A, B, and C. And A union B would be this is A union B. Okay, so you have seen this before, I'm quite sure. Anyone not seen this before? Venn diagram? Okay. You trying to be safe? Put your hand up. All right, it's called Venn diagram, okay? Basically just circles to represent sets. Move on to what we call inclusion, to include something. Exclusion, not include something. The principle of inclusion, exclusion. We can use notation n, small n of A, meaning how many members are in the set A. So if we have 2, 3, 6, 8, 9, so there are 1, 2, 3, 4, 5 members. So n, or the number of elements in the set A, is 5. So now the principle of inclusion exclusion states this. For any two sets, let's say A and B are two sets, the number of elements in the set A union B is number of elements in A plus the number of elements in B minus the number of elements that's common to A and B. Okay, so that's pretty obvious if you look at the visualization. So this is A. Number of elements in here, say, is 5. This is B. The number of elements in there, say, is 6. So now if you have A union B, this is and intercept, but it's union, that means combining these two would be the outline here with A and B. So what is it? It is this circle plus this circle, but this overlap part is represented twice. So you subtract it out. So if you visualize it, the area under these two circles is just this. It's this circle area minus this intercept area. So if you visualize it, then this formula makes sense. Very simple. So number of elements in A union B is number of elements in A plus B and then minus the common, because the common area has been counted twice. So as an example, A is a set of even numbers or natural numbers up to 100, and B is a set of natural numbers in increments of 5. So if you count those, number of elements in A would be 50, and number of elements in B would be 20. What's common? Now that you can do by matching, or you can use a formula to find what's common. But in either way, you'll find that there are 10 of them. So for example, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Those are the 10 numbers that are common between A and B. So the total number of elements in A union B, combining these two, would be 50 plus 20 minus 10, which is 60. Okay, so this is in the notes. If you need to review it later on, please do so, and make sure you understand it. And since I have uploaded the slides for next lecture and the lecture after as well, it would be a good idea perhaps for you to review all the slides quickly before the class next time. So then you can ask questions maybe. You can look at it, see what you don't understand. You can ask me in class next time. Oops, too much. Now we can extend that to multiple sets, not just 2 sets. We can have 3 sets, A, B, and C. A union B union C. So it's the same concept. You can visualize it from the Venn diagram. Basically, we have A plus B plus C. But then these areas are duplicated. You take them out. But the duplication of these 3 is this. So you have to add it back in. So you can visualize this using the Venn diagram. So try to visualize it yourself. This relationship, the number of elements in A, union B, union C, which means the whole area. So you take this, plus this, plus this, minus this, minus this, minus this, but this is common between these 3. You have to add this back in. Okay, so you can visualize it, justify for yourself. The formula is correct. Okay, so visualizations is actually a very powerful technique, especially for human, because we like to see things. We associate things by sight and sound as much, but sight is actually very important. So that's why I suggested you can actually look at the Venn diagram as a visualization. They'll help you to visualize. It's not a proof, but it is some way help you understand this. Okay, so next section we'll talk a little bit more about other operations for sets. What else can we do with sets? Okay, we can do what you see down here. Let's say we have 2 simple sets of numbers, 1, 2, 3, and then 3 and 5. We can do, well, it's a multiply sign here, or cross, A cross B. And then we have a special character called P, not this P, not the irrational number. That denotes a power set. Okay, this is described in the next slide. This cross product is called Cartesian. I'm confused with Star Trek. Cartesian, not the Cartesian product of A and B, and this is the power set of A. This is a description. So the cross product or the Cartesian product is described as A cross B. You take the element of A and element of B and put it together as an element. So this belongs to the A, and the second number belongs to B. So as an example, you can see these A cross B. You take element 1 here, 3 here, and then 1, 5. So take one element here, one element here. So all combinations of this. So the 3 elements here, 2 elements there, all combinations of elements is 3 times 2. So you have 6 elements in this cross product. Okay, in the Cartesian product, or the cross product, consists of a set of ordered pairs. In parentheses, we call these pairs. In order, because the order matters. 1, 3 and 3, 1 means different things. So in a set, remember, order does not matter. It can be 1, 2, 3 set, or 2, 3, 1, or 3, 2, 1, or 3, 1, 2. It's the same set. But in an ordered pair, we put in round parentheses, the order matters. 1, 3 is not the same as 3, 1. In other words, A cross B is not the same as B cross A. what would you get for B cross A? You would have to reverse. You have 3, 1, 5, 1, 3, 2, 5, 2. Well, 3, 3 is the same, but this is 5, 3, right? Would be the reverse. But the order matters. It's an ordered pair. So A cross B that's not equal to B cross A. It's like doing things in order. First, you get up, then you attend class. It's not the same as you attend class and then you get up. That means don't sleep in class, please. If you get up from class, then from sleeping in class, that means you're sleeping in class. If you do 1, 3, you get up, come to class, fine, good. But if you do 3, 1, that means you come to class, but you sleep. And then 1, you get up, you wake up after class. That means you're sleeping in class. So that's not what we want. It's not the same thing also. Okay, so power set. So in terms of the notation, we use this. So an order pair, parentheses, A and B, such that A comes from the set A, is an element in A, and B, lower b, is an element in the set capital B. Okay, so understand the notation, and this denotes an ordered pair. So the notation for ordered pair. And for power set, basically, is all subsets. Power set of A is a set such that this set is a subset. This is notation for a subset of A. So all subsets of A is called a power set. So the example here, A, so in this case B. B is 3 and 5. Subsets of 3 and 5 includes 3 and 5 itself. So this is a subset of this. Or set consists of only one element, 3. This is a subset of this. 5 is a subset of this. Or the null set, null or empty set, is also a subset of any set. So the power sets consist of all the subsets. So you have to list or find all subsets in whatever this is, B in this case. And the answer in this case is 1, 2, 3. There are 4 elements in here. Okay, so the notation is this. Power set. Yes?
The empty subset.
Empty subset.
Yeah, what does it explain?
What does it explain? What is the meaning of an empty subset? Okay. And why do we need to write it? Okay. So a subset means all the elements here is an element here. Right? By definition, all the elements in a subset has corresponding element in the set. So why is this empty set here? And what is the meaning of an empty set? An empty set is also called null, N-U-L-L, null set. A null set means it consists of nothing. No elements. So the question is this really a subset? Depends how you argue. You can say the complement of a set is null, nothing. Now, 2 things. First, let's go with definition. Definition is actually this. That means it's a subset. So now, if we say a null set is not a subset of any set, then it should not belong to the power set. Okay, so two things. One is first define what the null set is. The null set is an empty set that consists of no elements. Not the zero element, not just nothing in it. No members. Like I said, no one coming to class, or no one paying attention in class. I mean, absolutely no one. That means it's a null set or an empty set. Okay, so everybody knows what that means, right? Second one is the null set, is it a subset of a regular set? Is it an element of a regular set? So if you look at any set of numbers, for example, this set. Actually, maybe not. Okay, maybe that's not it. Let me back up. Maybe we haven't covered that yet. Okay, it might take a little bit more time. I want to cover some material first. So let me get back to you on this. So the question is, should this be the empty set, a null set, should it be part of, is it a subset of a set, of a regular set? So I'll get back to you on this. Let me just, maybe this will help better. For now, let's go with it being a definition that includes the empty set, okay, null set. Let's do some exercise first. So here we have A is this and B is that. How many elements? That means we're asking for n. N of this. A cross B and B cross A. So the number should be the same, even though the set itself is not the same. So A cross B, 3 elements here, 2 elements here. So 3 times 2, there should be 6 elements in here. And 6 elements in here. So 3 times 2 is same as 2 times 3, right? So it doesn't matter if you take the first element of the ordered pair is from A or from B. The number, so how many elements, that means the number of elements, would be the same for A cross B and B cross A. So both of these are the 6 will be 6. 6 and 6. 3 times 2, 2 times 3. And this one, A intersect B, is just one element. A union B, 4 elements. But we're not talking about number. We're talking about what the number is. Here is 3, and here is 2, 3, 4, 5. What about the cross? Its cross would be 1 element here, 4 elements there, 1 times 4, so it's 4. Right? So the elements here would be, the intersect is 3, so it's 3, comma 2 is 1, then 3, comma 3, 3, comma 4, and 3, comma 5. So these are the 4 elements in this set operation. So a set operation always gives you a set. The outcome is a set. It could be an empty set, but it's still a set. So power set of A, there are 8 of them. So how do we get 8? 2 to the power of 3. So why is it 2 to the power of 3? We have 3 elements, but why 2 to the power of 3? Okay, but do you know why? For a power set, yeah, you can quote the formula, but do you know how to derive the formula? Okay, so if you're looking at subsets of this, we're looking for all permutations, which you'll learn in stats course. Have you learned permutations? Okay, so we're looking at permutations. All permutations of this set. Okay, so you can review that, I guess. Same as B, and then A intersect B would be just the set with element 3, right? And the power set of that, 2 members, 3 and empty set, null set. So 2 to the power 1 is 2. Okay, there are more long faces, people not doing something else. That means some of you are confused. At least some of you are confused. Many of you are confused. So maybe it's not a good idea to go too fast. Well, what I recommend you to do is go over the material and then see if you understand it. And if you have questions, make sure you ask your friends or come ask me later. Okay, I'll try to, because like I said, most of this is supposed to be review for you. So that's why I go over a little bit faster. But then if there's something that is not clear, like the definition, then we'll go over that in more details a bit later. Okay, next we have another definition. It's called partition. So you probably all heard about the term partitioning your hard drive. You can have a DOS partition, if you know what that is, Windows partition. You can have a Linux partition. Basically, you separate it physically into compartments which do not overlap. So there's non-empty subsets of A satisfying. Basically, when you partition something, it's like this. These two are partitions. There's nothing overlap between each of these partitions. So partitions, each partitions have nothing in common. Basically, it's a pie. You divide the pie into so many pieces, and each piece to give someone to eat. The piece you eat does not contain the piece that I eat. It's all separate, right? So these are partitions. And if you take the union of all the partition members, then you should get the whole pie, or the entire set. Okay, and as an example, we have a set of natural numbers from 1 to 6. And this is a partition because it consists of 1, 2, 3, 4, 5, and 6. So it's a partition of A. There are 4 parts. This is a complete partition because all the members in A are taken into consideration. We can have, say, the whole set. This is actually a subset. It's the same set. But A is a partition of A itself. You can just divide into one partition. Like your hard disk can be one partition with just, you don't have to divide into C or D or E, but just C, say. Now this is not a partition because we have an overlap here of 3 in both cases. 1, 3, 4, 2 is fine, but then we have 3, 5, 6. This 3 and this. So these 2 partitions do not give an empty intercept. When you look at these 2, we have something in common. So this is not a partition. This is also not a partition. Why? This is again the tricky part. Because these are not sets. This is just number 1 and 2. So partitions are subsets. It's a set. So partition of a set A is a set of non-empty subsets. Okay? So an empty subset, the null set, is not a partition. But I'll explain again later. The null subset is a subset of any set. Okay? So this is not because 1 here is an element, it's not a set. And partition, by definition, again, partition is a set. So just be careful. And also here, it's not a partition because we define by definition an empty set. Oops. It's a set of S of non-empty subsets. So even though the empty set, the null set, is a subset, but definition of partition does not include the non-empty, does not include an empty subset. It has to be non-empty. Empty doesn't count for partition. So that's why this is not a partition. These 2 is, if you remove this, then it's fine. But if you add this empty set in there, then it's not partition of A. Okay? Now you can say this would be confusing, which could be because it's notation. And you might wonder, why do we want to work with notations like this? Well, that's because quite often we cannot list all the members of a set. It can be very large, right? Like these. These are all infinite sets. You cannot list it. So we use notations. This is the part that some of you would get confused, for sure, because just as proofs and more formal methods, more formal ways of representing mathematics and so on, can be confusing in the sense that you think it's difficult, but just approach it one step, small thing at a time. Look at it. So what do we see here? the first line here, first example, we have the squiggle brackets, which means it's a set. We use this to indicate set. Now, in this set, how many elements are there? There are 1, separated by comma, 2, comma, 3. The 3 elements in that set. Okay, just approach it one step at a time, see what you understand, and then it is actually what it seems. So we want to ask the question, which of the following are partitions of Z, which is Z of integers, which runs from negative infinity number to positive infinity, but they are integers. So now, first one, remember our notation before. We take, this is a set notation. The condition is that n belongs to set Z, set of integers. And this set consists of, if you put all the integers in here, say start with 0, you get 1. Put 1 in there, you get 4, and so on. We'll give you this. The next one is 3n plus 2. So now, I already gave you the answer. And then next one is just 3n. So I already give you the answer, actually. Okay, first, read the question. Which of the following are partitions of Z? A partition means this subset plus this subset plus this subset. They have to be all distinct, no overlapping, right? So there's nothing in common between this and this, nothing in common between this and this, nothing in common between this and this, and so on. But from what I just told you, you can answer the question already. If you look at this, you can say, okay, it's 3n plus 1, 3n plus, you have 3n, 3n plus 1, 3n plus 2. It seems like maybe it's partition. But is it? It is? Okay, another way to look at it, just imagine you have all set of integers. You partition the integers into 3 partitions. And are these distinct? So either the integer is divisible by 3, that means belongs to here. If integer is divisible by 3, it belongs to here, right? This is 3n. All the numbers multiplied by 3, that means all the numbers from this subset are divisible by 3. So you have all divisible by 3. And then now you have the other 2. Are these divisible by 3? They're not, because it's divisible by 3 plus 1, divisible by 2 plus 2. If you divide this by 3, you get, fine, this is fine, but this is a rational number. This is a rational number. So these 2 are not divisible by 3. So for sure, this and these, this and these 2 together forms a partition for sure. So now the other question is, are these 2 distinct? 3n plus 1 and 3n plus 2. So if you look at example, if you cannot visualize it, so examples here would be 1, 4, 7, 10, and so on. And examples here would be 2, 5, 8, and so on. So what it means is, if you imagine, is counting. This we start counting at 0. If you just look at positive. This we start counting at 1. This we start counting at 2. And we count every 3. So are they distinct? It should be, right? Because divided by 3, you have 3 different sets. And 1, you start at 0, 1 start at 1, 1 start at 2. And the next one is a 3. 3 belongs to here. And then 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on. So divisible by 3 and increment by 1 at a time, that means they are in fact distinct. That means, yes, this is true, that these 3 subsets form partitions for a set of integers. Next one. Six n, 3n plus 2, 2n plus 1. Can you think of instances when there's... So the easiest thing to find they're not partitions is to just find one counterexample. Can you find one example that an element in here is the same as an element in here, or same as an element in there? N is minus 1, and then for which one? This is minus 1. When n is minus 1, you get 1. When n is minus 1, you get 1. Right? So that means 1 is here, 1 is here. That means they're not distinct. So all you need to do is find one counter example, and then you can disprove, or you can say, this is not true. Okay, so as an exercise, you should try to go through these two yourself and see if you actually determine if they're actually partitions of set of integers. Okay? Now, I will not go into proofs. I'll wait till next time. It's almost time anyways. So what we've done so far, actually, we can actually prove if these are actually partitions in a more rigorous, formal way. So like I said, it's easier to disprove, which is a way of proving. To disprove something, if you can disprove it, that means it's not true. That's one of the easy ways to prove or disprove something. But does not mean you can prove it, but if you can find a disproof, then you know it's not true. Okay. So you already talked about proofs in this course, right? In some other examples, but not specifically for sets. So this is one thing, for example, we can use proofs. And we're going to prove some of these properties of sets. So we look at more properties, and we look at operations, and we're trying to prove it more formally. Okay, let me just say one thing on the question that was asked earlier as to why an empty or null set is a subset. Well, a null set or empty set is partial proof, consists of, what's the number of elements in a null set? 0, right? So in a set, it can consist of, there are 3 elements here. You can pick one element, you can pick this element, this element, this element. You can pick 2 elements, you can pick all 3 elements, or you can pick no elements. So this is a way, sort of hand waving for now, but what I'm saying is, if you take the complement of this 1, 2, 3 together, you can say it's a null set. So in that sense, a null set is also a subset of this. If you break it into partitions, then null set does not count because it's by definition. But a null set also has a number of 0, no elements in it. So if you imagine I ask you to choose something from here, you can say I choose nothing. So that is something you can choose. So in that sense, it's a subset. Okay, so I'll leave it at this for now. Think about it. And then we'll go into proofs and also move on to functions and relations next week. Okay, so I suggest you review the material before you come to class. And then I'm sure you have questions. And then you're trying to listen. And hopefully I can answer your questions during my lecture, in my lecture. If not, you can ask me trying to clarify as well. Okay? All right, that's all for today. See you guys next week.